Hello everyone, my name is Naina and I'm from the Buddhi Academy. So in our previous video we have seen the chapter hydrocarbons. In that we have seen alkenes and some properties of them, alkenes, and now in today's video we will learn about alkynes. Now alkenes are with single bond whereas alkenes are with double bond. Alkynes are a bit further, that is with triple bonds. So today we will learn about alkynes, their preparations and some of their properties like physical and chemical. Now alkynes, like alkynes are also unsaturated hydrocarbons, okay, because they contain at least one triple bond between them, okay. Now, the number of hydrogen atom is still less in alkynes as compared to alkenes or alkanes. Their general electronic or their general formula is CnH2n minus 2. Now, for alkanes, okay, for alkanes it is CnH2n plus 1. For alkenes it is CnH2n, whereas for alkynes it is still less, it is CnH2n minus 2. Okay, so compared to alkenes and alkanes, alkynes has the number of hydrogens less. Okay, the number of hydrogens is less in alkynes compared to alkenes and alkanes. Now, the first stable member of alkyne series is your ethyne. Okay, is popularly known as acetylene. The first stable member of alkenes was ethylene or your ethene. Now, again, the first stable member of your alkyne is also your ethyne, popularly known as acetylene. Okay, now acetylene is used for arc welding purposes in form of oxyacetylene flame obtained by mixing acetylene with oxygen gas. Now acetylene, it is popularly or it is used in your arc welding, okay, welding an arc. Now how it is used? It is used in the form of oxyacetylene, that is you flame your flame obtained by mixing your acetylene with oxygen gas, okay. Now alkynes are starting materials for large number of organic compounds, okay. Alkynes are the starting material for large number of organic compounds, hence it is interesting to study this class of organic compounds. Now first we will learn about their nomenclature and isomerisms. Now for alkanes it always ended with ane, alkenes it is ene, for alkynes it will be yne. Okay, in common system alkynes are named as derivatives of acetylene, okay. Now in IUPAC system they are named as derivatives of the triple bond is indicated by the first triply bonded carbon. Now how you will represent the position of your triple bond? The position of your triple bond is indicated with your first triply bonded carbon. The common name of few members of alkyne series are given below the table. As we go down, I'll show you the table. Now, you have already learned that ethyne and propyne have got only one structures, but there are two possible structures for butane. Okay, that is but1-ine and but2-ine. You can get the triple bond position on the first carbon also, on the second carbon also. For propyne and ethyne, there is only one structure, but whereas for higher ones you can get more than two structures. Since these two compounds differ in their structure due to the position of triple bond, they are known as position isomers. Okay, so but1-ine and but2-ine, since the triple bond changes its position from 1 to 2, they are called as position isomers, and the phenomenon is position isomerism. Now, how many ways you can construct the structure for the next homologue, that is the next alkyne, with molecular formula C5H8, okay, that is your pentyne. Your pentyne can have three structures, okay. One will be your pent1-ine, second will be your pent2-ine, and third will be your 3-methyl but1-ine, okay. one of the third carbon. Okay, 3 methyl but 1 ine. Okay, now structure 1 and 2 are position isomers. Okay, 1 and 2 are position isomers because the triple bond is on first carbon and second carbon, and the structures 1 and 3 or 2 and 3, either these two or these two. Okay, they are chain isomers. Okay, differ in the chaining system. Now this table, here you have common and IUPAC names. For ethyne, your common name is acetylene. For propane, it is methyl acetylene. For butane, it is ethyl acetylene. For but2-ine, it is dimethyl acetylene. Now you can see the end part remains as acetylene only. Now for propane, it is methyl acetylene. Why for it is methyl acetylene? Because for propane, this is your acetylene molecule, right? You have added a methyl group here, so that's why it is methyl acetylene. Again CH3CH2, that is C2H5. This is your ethyl acetylene. Now this is your acetylene molecule. Both the sides you have methyl group. That's why it is dimethyl acetylene. Okay, this is how the naming or the isomerism of your ethyne molecule or alkyne molecules are. Next one is your structure of triple bond. Okay, ethyne is the simplest molecule of alkyne series. So let's start with the structure of ethyne molecule. Now each carbon atom of ethyne molecule has two sp hybridized orbitals. You know the hybridization, right? sp3 for single bond, sp2 for double bond, and sp for triple bond. So ethyne molecule, the carbon will be sp hybridized. Now carbon-carbon sigma bond is obtained by the head-on overlapping of two sp hybridized orbitals. Okay, so the head-on overlapping of two sp hybridized orbitals of the two carbons of ethyne molecule. Now the remaining sp hybridized orbitals of each carbon atom undergoes overlapping along the internuclear axis with the 1s orbitals of each hydrogen atoms, forming the 2CH sigma bonds. Okay, now the remaining will be your unhybridized p orbitals that are joining perpendicularly. To this you will add hydrogen, and the later double bond is formed by your two parallel unhybridized p orbitals which are perpendicular to each other. Okay, the two p orbitals of one carbon atom parallel to 2p orbital of the other orbitals of other carbon atom which undergo lateral or sideways overlapping to form the two pi bonds between carbon atoms. Okay, so here you can see this is the sp-sp hybridized head-on overlapping of the carbon atoms. Then you have two hydrogen atoms. Okay, the remaining p orbitals of this carbon atom. Okay, there are two p orbitals which are unhybridized. These two p orbitals, what they do is they overlap with each other. Okay, they undergo lateral or sideways overlapping to form the pi bonds, which is shown here. Okay, they undergo a lateral overlapping to form the pi bonds. Thus ethyne molecule consists of one cc single sigma bond and two ch sigma bonds, and again two cc pi bonds. So what are the bonds that are consist in your ethyne molecule? Ethyne molecule has a cc single sigma bond, two ch sigma bonds. Okay, so this is your cc sigma bond, this is your ch sigma bonds, and then you have a cc pi bonds, that is 2 cc pi bonds. Now the strength of the C triple bond C is more than those of the ethyne as well as your ethane molecules. Okay, so the triple bond is more stronger than your double and single bonds. Now the triple bond length is shorter than those of the double and single bond. Okay, the bond length is also shorter. Electron cloud between two carbon atoms is symmetrical, but the internuclear axis, about the internuclear axis, the electron cloud is cylindrically neutral around the internuclear axis. Thus ethyne is a linear molecule. Now preparation, how you can prepare your alkyne molecules from calcium carbide. Okay, you can prepare your alkyne molecules from calcium carbide. On industrial scale, ethine is prepared by treating calcium carbide with water. Calcium carbide is prepared by heating quicklime and coke. Now, how you will form calcium carbide? Okay, calcium carbide is formed by treating quicklime with coke. Okay, quicklime can be obtained by heating limestone as shown in the following. Now, first you have to prepare your quicklime. Now, quicklime is prepared by treating calcium carbonate. Okay, heating calcium carbonate, you get your you get your quicklime. Okay, this is calcium carbonate. Calcium carbonate on heating gives you quicklime and carbon dioxide. Then your quicklime is later treated with 3 carbon atoms forming calcium carbide. Okay, then calcium carbide, when you treat it with water, you get calcium hydroxide and C2H2, that is your ethine molecule. This is how you form your alkyne or ethine from your calcium carbide. Now next is from the vicinal dihalides. Again, this is your vicinal dihalide. Vicinal dihalides on treatment with alcoholic potassium hydroxide. It is alcoholic potassium hydroxide dissolved in alcohol. Undergo dehydrohalogenation. Like what happens in ethene, same thing happens here also. Okay, when you have alcoholic potassium hydroxide, when you react it with your alkyne or ethine molecule, you get when you treat it with vicinal dihalide, okay, you get dehydrohalogenation. Okay, with dehydrohalogenation you convert your alkane into alkene. Okay, one molecule of hydrogen halide is eliminated to form alkynyl halide, which on treatment with sodamide gives alkyne. So when first what you have to do is you have to take the vicinal halide, you have to treat it with alcoholic potassium hydroxide. What will happen? You will get your dehydrohalogenation. Okay, and you get your ethene from alkene. You have converted into ethene. Now this ethene, when you react it with sodamide, that is sodium and amide, sodamide, you get your alkyne. Now properties of alkynes. Physical properties of alkynes follow the same trend of alkenes and alkenes. Okay, their physical property also follows same trend with your alkenes and alkenes. First 3 members are gases, the next 8 are liquids, and the higher ones are solids. Okay, now all alkynes are colorless. Again, they are colorless. Now ethine has a characteristic odor, other members are odorless. Same thing what happens with your alkenes is what happens with your alkynes. Okay, they are all colorless. Okay, ethine will have a characteristic odor, smell, and other members are odorless. Now alkynes are weakly polar in nature. They are lighter than water and immiscible with water but soluble in organic solvents like ethers, carbon tetrachloride and benzene. So alkynes, they are weakly polar in nature, they are lighter than water, hence they are not immiscible with water. They doesn't mix with your water, but they are soluble in organic solvents like ethers, carbon tetrachloride and benzene. Their melting point, boiling point and density increases with increase in molar mass. Again, the number of CH2 molecules will increase your melting point, boiling point and density. Okay, these are the physical properties. Next are the chemical properties. Now, alkynes show acidic nature, addition reaction and polymerization reaction as follows. Okay, first, acidic character of alkyne. Sodium metal and sodamide, that is NaNH2, are stronger bases. They react with ethine to form sodium acetylide with the liberation of dihydrogen gas. So when you have sodium metal and sodamide, these are strong bases. Okay, when they react with ethine, they form sodium they leave dihydrogen gas. This reaction have not been observed in case of ethyne and ethane, thus indicating that ethyne, okay, whenever you have ethene and ethane, they doesn't react with sodium metal and sodamide, but ethyne they do react with sodium metal and sodamide, and in this reaction they form sodium acetylide, liberating dihydrogen gas. Okay, now this indicates that ethyne is acidic in nature in comparison to ethene and ethane. Since sodium metal and sodamide are strong bases and ethyne can react with them, forming sodium acetylide and liberating dihydrogen gas, this indicates that the ethyne is acidic in nature compared to ethene and ethane. Okay, now hydrogen atom in ethyne are attached to the sp hybridized carbon atoms, whereas they are attached to sp2 hybridized carbon atom in ethene and sp3 hybridized carbon atom in ethane. Now as we've done the structures of alkane, alkene and alkyne, we have seen that the hydrogen atoms, they are attached to the carbons which are hybridized. For example, in alkane, the hydrogen atoms are attached to that carbon which are sp3 hybridized. For alkenes, the carbons are sp2 hybridized and the hydrogens are attached to them. And now for alkynes also, the hydrogens are attached to that carbon which is sp hybridized. Due to the maximum percentage of S characters, the sp hybridized orbitals of carbon atom in ethyne molecule have highest electronegativity. Hence, this attract the shared pair of electrons of the CH bond of ethyne to a greater extent than that of sp2 hybridized orbital of carbon ethene and sp3 hybridized orbital of carbon in ethane. Now, you know, sp hybridization, both in this case, the molecule, the orbit will have 50% of S character and 50% of P character, right? Now, in this case, ethyne molecule have highest electronegativity because it has 50% of S character. So, the electronegativity also increases. Hence, because of this high electronegativity, the shared pair of electron of the CH bond of ethyne is to a greater extent. So the CH bond which is there in the ethyne molecule, the electron pair which is involved in that CH bond is attracted more towards the carbon because of the electronegativity. Okay, and this is greater than the sp2 hybridized carbon or sp3 hybridized carbon of ethene and ethane. Thus, in ethyne, hydrogen atoms can be liberated as proton more easily as compared to ethene and ethane. Now, because the carbon will pull the electron towards itself, the hydrogen will have a partial positive charge, and because of this, the hydrogen can be liberated as a protons more easily compared to ethene and ethane. Now, since the ethyne molecule can liberate hydrogen, it acts as a acid. Okay, that's why it reacts with sodium metal and sodamide. Hence, hydrogen atoms of ethyne attached to triply bonded carbon atom are acidic in nature. Okay, that's why they react with base. So here, this is your ethyne molecule. When reacted with sodium, one of the hydrogen is removed and the sodium is added. So this is a monosodium ethanide with half of the hydrogen liberated. Now, when you have monosodium ethanide reacting with another sodium molecule, this gives you a disodium ethanide. So again, half H2 is removed. Okay. It reacts with your sodamide. Okay, this is your sodamide. With sodamide, H2 and your ammonia is formed. Now these reactions are not shown by alkenes and alkanes. So this type of reactions you will never observe with alkanes and alkenes. Hence used for distinction between alkynes, alkenes and alkanes. Hence these reactions are used in the distinguishing as a distinguishing point between alkynes, alkenes and alkanes. Now, we have seen about the propynes and ethynes. Now what about the butynes? Alkenes, alkenes and alkynes follow the following trend in their acidic behavior. Okay, alkynes are more acidic than alkenes than alkanes. Okay, so this will remain same. Now this is between alkenes, alkenes and alkenes. What about the trend in alkynes only, higher alkynes? Okay, so here ethyne is more reactive than propyne, then your butane. So butane is less reactive. Second one is the addition reaction. Now alkynes contain a triple bond, so they add up two molecules of dihydrogen, halogen, hydrogen halides, etc. Addition reaction, you are adding something to your alkynes. Since alkynes have a triple bond, they can add up two molecules of dihydrogen, halogen, hydrogen halides, etc. Now formation of addition product takes place according to the following step. Okay, how your addition process takes place. Now this is your ethyne, this is your consider this to be your hydrogen halide. Okay, now you will get an ethyne first, then you will get your alkyne converting into your alkene. Okay, it is a vinylic cation. Now, the addition product form depends upon the stability of vinylic cation. Addition in unsymmetrical alkynes takes place according to Markovnikov's rule. Now this is a symmetrical alkyne. Symmetrical alkyne, it depends on vinylic cation, whereas unsymmetrical alkynes takes place according to your Markovnikov's and anti-Markovnikov's rule. The majority of the reactions of alkynes are the examples of electrophilic addition reaction. The majority of them are electrophilic addition reaction, where your reagents or the addenoms are electron deficient. Now first one is the dihydrogen, addition of dihydrogen. Now dihydrogen can be added with the presence of platinum, palladium and nickel. Okay, now first when you add dihydrogen, you will convert your alkyne into your alkene, and again when you add dihydrogen, you can convert it into your alkane. So here propyne is converted to propene and then to propane. This is how your hydrogen is added. The second one is your addition of halogens. Okay, addition of halogen, both the carbons will get 1 bromine each. Okay, so it is 1,2 dibromopropene. So first your propyne will convert into propene, and then again when you add 2 more bromine, it will convert into 1,1,2,2 tetrabromopropane. Okay, now the reddish orange color of the solution of bromine in carbon tetrachloride is decolorized. This is used to test for the unsaturation. So here this is used for the test of unsaturation. Next one is addition of hydrogen halides. Now 2 molecules of hydrogen halides are added to alkynes to form a gem dihalides, in which 2 halogens are attached to the same carbon atom. Now gem dihalides mean, now these are vicinal dihalides, right? Gem dihalides means you are adding the bromine to the same carbon atom. Okay, for example CCC, Br. So this is a gem halide. Okay, when both the halogens are added onto the same carbon atom. Now here this is your ethene, HBr, you get bromoethene. This is your ethyne molecule with triple bond. When you add HBr, you get a bromoethene. This is a symmetrical molecule, right? So wherever you add, it doesn't cause much difference. Then again, when you add HBr, same thing will happen. You will have 1,1-dibromoethane. Okay. When you have a propene molecule which is asymmetrical, it will add according to Markovnikov's rule. So the Br will add to that carbon which doesn't has a hydrogen. So it will be 2-bromopropene. Then again Markovnikov's rule, again add your HBr. The bromine will add to that carbon which doesn't has an hydrogen, Br. So it will be 2,2-dibromopropane. Okay, so this is a gem halide. This is a gem halide where both the halide groups are present on same carbon atom. Next one is the addition of water. When you add water, like alkenes and alkenes, alkynes are also immiscible and do not react with water. Okay, so alkynes also doesn't react with water, alkenes also doesn't react with water. Similarly, your alkynes also doesn't react with your water. However, one molecule of water adds to alkynes on warming with mercuric sulfate and dilute sulfuric acid at 333 Kelvin to form your carbonyl compounds. But what will happen on warming? Okay, one water molecule is added to your alkyne molecule. When it is added, when you warm it with mercuric sulfate and dilute sulfuric acid at 333 Kelvin. Now, it forms a carbonyl compound. So, when you have ethyne, when you add water to ethyne and you react this mixture in the presence of mercuric sulfate and sulfuric acid at a temperature of 333 Kelvin, you get an CH2 CHOH. Okay, this is the alcohol, right? Now, isomerization of this, you will get ethanol. Okay, you get aldehyde. Now, next one is the propine. Okay, propine, you get propanol, propan to all, but isomerization of this, you will get propanone. That is your ketone. So, symmetrical, you will get an aldehyde. Non-symmetrical, you will get a ketone. Next one is the polymerization. Okay, you have a linear polymerization. Now, under suitable condition, linear polymerization of ethyne takes place to produce polyacetylene or polyethylene, which is a high molecular weight polyene containing repeating units of CH double bond CH, CH double bond CH, and can be presented as like this. Under special conditions, this polymer conducts electricity. Okay, now linear polymerization means it is under suitable condition. Okay, linear polymerization of ethyne takes place. Okay, you join all the ethyl molecules in a line. Okay, linear polymerization of ethyl molecules takes place. It produces polyacetylene or your polyethylene, which has a high molecular weight, polyene containing repeating units of this structure. This is the polyene, which is a repeating unit for polyethylene or polyacetylene structure. Okay, now under special conditions, this polyacetylene or polyethylene can conduct electricity. Okay, now thin film of polyacetylene can be used as electrodes in batteries. These films are good conductors, lighter and cheaper than the metal conductors. Okay, now thin films of polyacetylene can be used as electrodes in batteries. So polyacetylene, a thin film of that can be used as electrode in batteries. Now these films are good conductors. Because they are good conductors, they are used as electrodes in batteries, right? Good conductors, lighter and cheaper than the metal conductors. Okay, next one is the cyclic polymerization. Now ethyne, on passing through red hot iron tube at 873 Kelvin, undergoes cyclic polymerization. So ethyne, when you pass it through a red hot iron tube at a temperature of 873 Kelvin, undergoes a cyclic polymerization. Now, three molecules polymerize to form benzene, which is the starting molecule for the preparation of derivatives of benzene, dyes, drugs, and large number of organic compounds. This is the best route for entering from aliphatic to aromatic compounds. Okay. Now, when you have three molecules of ethyne, okay, three molecules of ethyne, when you pass them to red hot iron tube at 873 Kelvin, they will form your benzene. Okay, now this is the step where we convert where we enter from aliphatic to aromatic compounds. So this is a straight chain aliphatic compounds which on treatment has formed a aromatic benzene ring. Okay, so this is what happens with your ethyne molecules. Now next will be your aromatic hydrocarbons that we will do in our next video. I hope you all have understood about about alkyne molecules, the structure, nomenclature, isomerism, properties and the reactions involved in the alkyne molecules, also the preparation of your alkyne molecules. So thank you for watching my video. Please do like, share and subscribe to our channel.